Hi everyone, welcome to my channel. Make sure you subscribe if you enjoy my explanations. I solve LeetCode daily challenges and also I try to solve weekly contests and bi-weekly contests. Let's take a look at today's problem. If you read just the first sentence of this problem, you should guess, oh, this is a graph problem because we have n cities connected by some number of flights. So we have nodes and we have edges. And then you go on to read that we have a list of the edges, the flights, and from to, and then you here understand that the graph is weighted actually, and you have all of the edges from to price I. That's it. And actually, if you look at this diagram, you can also figure it out that this is a graph problem. And then you are given a source, a destination again, and k, and number k, and you should return the cheapest price from SRC to DSD with at most k stops. Okay, this is a modification of the classic shortest path problem on a weighted graph. If you have seen, let's take a look at the first example and then we will discuss the solution. So we have n equal to 4 and k is equal to 1, and we want to go from node 0 to node 3. So here from 0 to 3, and we can do at most one stop. So this is the best one. This is the best route. Okay, but if we are allowed to do 2 stops, we can take the other routes, 0, 1, 2, 3, which is 400. But that's not the answer. The answer is 700 because we can make at most one stop. So if we get rid of the k, for a moment, this is a very classic problem. You can just run any of the algorithms you know, like Dijkstra, like Bellman Ford, or even Floyd-Warshall in this example, because the number of nodes is only 100 and Floyd-Warshall is n cube, and then you're done. But here we have something, this limitation of k. So the first thing you should be asking yourself is, do I know these algorithms or not? If you don't, then you should pause this video and go and learn about them, or skip the first part, which I'm talking about these common algorithms, and go to the next section, which I'm explaining, where I will be explaining the recursive solution, thinking recursively about this problem without having any prior knowledge of the graph algorithms. So this is how I want you to approach this problem and ask yourself, do I have the tools to solve this problem? Okay, let's go and take a look. If you have heard about Bellman Ford algorithm, okay, a simple modification to Bellman Ford algorithm can solve this problem. This is the Bellman Ford algorithm. Okay, it does something n times, n minus 1 times, and that something is relaxing all of the edges. So this inner for loop is checking all of the edges and is updating the distance for the node on that edge. Okay, for this distance of v is getting updated, and it's doing this n minus 1 times. You just need to modify this algorithm, for example, and modify this one and just do that k or k plus 1 times. Go and think about it, why you need to do k plus 1 times. I can give you the answer, but then you are going to forget it. And my goal here in this channel is not to give you the answer. I'm aiming to talk about the process that you can take to come up with the answer. And that's how you are rebuilding, you're restructuring your mind to be able to become a great problem solver. You get some hints, and then you go and modify that and work with it and take a few minutes, a few hours even, and solve it. Let's go to the next one. So this is the first one. So learn about Bellman Ford and see how you can modify it. The modification goes to this for loop and see how you can solve it. So the next algorithm is Dijkstra. This is again the classic Dijkstra algorithm. Again here, you are not considering the number of stops. You can add that. If we look at this problem, like we have, look at this code, So here we are adding the nodes to the queue. So here, instead of adding the v to queue, we should add like v and 0, for example. V is the node and 0 is the number of stops that have taken so far to arrive at v. Okay, does that make sense? So we are modifying this Dijkstra algorithm and saying, hey, you know, from now on, the nodes look like this. It's not just the node index, it's also the number of stops. Okay, and then here, when you pop them from the queue, okay, when you pop them from the queue, if number of stops is greater than k, you ignore them. You just ignore them. So the pair that you just popped from the queue, you just ignore it. That's it. And then you have your answer. And also, you should also modify this distance. The distance should not be just distance v, it should be two-dimensional. It should represent what you are adding to the queue, your priority queue. Okay? So this is the case when you are implementing a Dijkstra and you are changing what you are adding to the queue. Most of the time, you should also change the distance. So distance should become distance of v and stops. So two-dimensional. And this means the minimum distance that it takes to go from SRC to v and do at most a stops number of stops. Does that make sense? Okay. And then here again, you should update it when you are adding something to the queue. Here, you should also consider that number of stops. Okay, so let's say you have solved it with Bellman Ford, you have solved it with Dijkstra or not, and now you want to, you know, think about this problem without having the framework of these algorithms. How do I think about this problem if I don't know about Dijkstra or Bellman Ford? Let's talk about that. Okay, so this problem, if you look at k, this number k is shouting, is telling you that, hey, think about me recursively. Oh, interesting. What do you mean? So let's say we have a function that can calculate the distance, and that function is called dist node and k, which is actually calculating what the problem is looking, going from SRC to node with at most k stops. So now let's think about this recursive. And what do I mean by recursively is that we can solve this problem based on a smaller subproblems. And obviously smaller subproblems here is referring to the number of stops. So k minus 1, right? So one of the answers for dist node and k could be dist node and k minus 1. So that means, hey, you want to arrive at node with at most k stops? Okay, first let's go and consider arriving at node with k minus 1 stops. That is an answer, right? That is a candidate. That's not an answer. That is a candidate. What else do we have? Let's say we have node here. Let's take a look at the graph. And then we have edges from A to node. This is direct edge with cost 1. And we have B to node with cost 2. Okay. So again, if you want to think recursively in this case, you can say, hey, I want to arrive at node with at most k stops. So that means I can arrive at A with at most k minus 1 stops. So that should be dist of A and k minus 1 plus this cost. So you arrive at A with at most k minus 1 stops, and then you pay this cost 1 to arrive at node. Okay, and that would be cost 1. Or for B, this of B and k minus 1 plus cost 2. That's it. And then you take the minimum of these three. And you have your answer. This is a recursion formula. We could solve this of node and k based on smaller subproblems. Now we should go and think about the base case, because whenever you have a recursive function or recursive formula, you should think about the base case. Okay? So what is the base case? The base case could be distance of node and 0. So that means what is the minimum cost to arrive at node if you can make at most 0 stops? That means you should go to node directly. So we have a few cases. So if node is already SRC, so if node is SRC, so we return 0. That's obvious, right? We are already there, so there's no cost. If there exists an edge SRC and node exist SRC and node, an edge, like this is an edge. If exists this edge, then return cost of this node, cost of SRC and node. Otherwise, return infinity, because you cannot reach that node with 0 stops. There's no way. Make sense? So this is the base case, and we have the recursive formula. Let's go and implement this dynamic programming approach. So what do we need? We need a dist function. Then we need to implement the base case. And we need to save SRC in one of the class variables. And then the other one, we need to check all of the edges. So we need to save this one in the class as well. Or instead of that, let's do something. Let's go back here. Do you see here A node, B node? This is the reverse adjacency list. So node needs to know which other nodes have an edge to this node. Okay? So let's create the reverse adjacency list. Okay. So we have a vector of pairs of ints and int and int. That means each node has a vector, and each member of that vector is a pair. And one of them is the node, one of them is the cost. So if I go back here, A and cost 1, B and cost 2 will be saved in the reverse adjacency list of node. Okay, so that's it. So we have n of them, vector pair of int and int, and it's empty. We don't have anything here. And then we do iterate over our edges. That's it. Now we have the reverse adjacency list. Let's go here and do an iteration over the reverse adjacency list of node. So here we are checking if node has an SRC. That means if there is some direct edge from SRC to node, return e.second, which is the cost here. You see, the second is the cost, the first is the node. And then here we just return infinity, because we couldn't find a direct edge from source to node. And we define infinity here to be a big number that is bigger than 10 to the 4 times 10 to the 2, so that we can have 10 to the 8 or something. Okay, now let's go here and solve the rest of it. So this is the base. This is solving this problem, node and stops -1, and then we can do another for loop over the reverse adjacency list. And sorry, this is not e. Yeah, e dot first, e dot second. Okay, here we can say result equals the minimum of result and this of e dot first and stops -1 plus e dot second. So that is the node, that is the edge, that is the cost. Okay, and then here return result. So we just need to memorize this answer so we don't get time limit, but let me just check if I'm doing everything right for now. We should return something. Okay, here we return this of DST and K. Okay. That's it. So let me memorize this. So we need a vector of DP. And we need to do this. dp.resize. How many of them? N of them. And a vector of int. And the size should be k plus 1 and -1. So this is how we initialize that. So here we go back. If dp of node and stops is not -1, just return it. And here, save it before returning. That is how we memorize. Okay, submit. Wrong answer. Oh, sorry. So if there is no path, we should return -1. Here, read the problem statement. Okay, here, yeah. If there is no such route, return -1. So here we should check if this is inf, return -1, otherwise return this stuff, DST and K. Okay. Awesome. Let me know if you have any questions, and please do follow and subscribe. Follow? Yeah. Subscribe and let your other friends know if you enjoy my explanation. Thank you very much.